Alright, so yeah, just a little bit about the series. Obviously we had part 1 back on the 9th of February covering hardware recommendations and tweaks. If you missed that, you can download it through or view it through the MyEnterCAD tool. If you need to find out how to do that, please email me after the webinar and I can provide some instruction on that. This webinar should be available through the MyEnterCAD within the next 24 hours, so should you wish to revisit it again, you can do so through that medium. Part 3 on the 13th of July is going to cover the drawing aspect of large assemblies, and Part 4 on the 7th of September we'll look at some specific tools you can use for large assembly modelling. And anything we've not covered in the other 3 sessions. I've already had a request for discussions regarding large assembly modelling in conjunction with EPDM and or PDM Pro. Plus we should be out of the 2018 beta program, and hopefully we'll be able to highlight any improvements that may be coming for the next major release. Moving on to today's agenda. What we're going to cover is looking at SOLIDWORKS capability. What SOLIDWORKS been capable of in the past and what can you expect to do in the current release, and I guess we'll look at that in terms of the sheer number of parts that SOLIDWORKS can handle. Component impact, parts of the foundation of assembly, so how do they impact the assembly performance. Assembly complexity, what makes up an assembly and by extension a large assembly. We'll have a look at assembly file loading, what's happening in SOLIDWORKS when we click the open button. And we'll have a look at some technologies and options that we can employ there to assist in opening those large assembly files. Then we'll move on to mates and how they impact large assemblies, some interesting information in that section. If I get time, we'll have a look at file versions, so what happens when your files are not at the latest release. And then finally we'll have a look at some common issues, things to look out for when building and working with large assembly models, and really that'll be a kind of summary of things that we cover in the webinar today. So let's get into the content. The SOLIDWORKS capability, so looking around about 10 years ago, we had customers building assemblies with up to 120,000 plus parts. In 2013, 184,000 parts, and in 2015 there was one customer in Australia. It wasn't our customer, but through our network I understand that there was one that had one with over 1 million parts in there now. And the only way he was able to achieve that was using best practices. I guess the point of the slide is to provide you with some confidence that you can achieve what you need with the SOLIDWORKS software in terms of large assembly modelling. Some of you may be struggling to perform with much smaller large assembly models. I guess what's required here to be successful is to provide or apply those best practices, and the aim of these large assembly webinars is to provide you with those best practices as guidelines on how SOLIDWORKS software works and how to work most effectively within those guidelines to achieve what you require. So let's take a look. And firstly, we've got the component impact. So what is a part in SOLIDWORKS? A solid model is the most complete type of geometric model used in CAD systems. It contains all wireframe and surface geometry to fully describe the edges and faces of the model. In addition to that, geometric info, it also has information called topology, and that relates the geometry together, so where a surface meets an edge. So typically in the old wireframe modelers, if you wanted to add a fillet onto an edge, you had to move everything manually. Solid models don't require that, so it makes it easy to apply things like fillets and draft, etc. Configurations are also part of components or parts, and you know, how many different versions of that part are within that part. Is that data cached or purged? any of that information can affect assemblies, and hence large assemblies. One other aspect of parts is the tessellated graphics. We don't normally see this in SolidWorks, and I did mention this briefly in the first webinar. But if we have a look at the two examples I've got there on screen, there's a block there. It's basically a six-sided face. It's got two triangles per face, resulting in 12 triangles. The bolt, which is probably not that much more complicated, it's just a couple of cylinders and a flange, by comparison has 5,850 faces on it. So it doesn't take much to increase that complexity in the tessellation. And I guess the key thing about it is that the CPU is generating all of that information, not the graphics card. Once that information's been generated, then the graphics card takes over to do your zoom, pan operations, etc. So I guess I'm going to switch to SolidWorks now. I just want to give you a quick demo, and I'm just waiting for that to switch over. Hopefully everyone can see that. Looks like it's gone to 100% on the audience view now, so you should be able to see that. If we go to the system options and document properties, and then the image quality page, you've got a slider at the top here showing shaded and draft quality for hidden lines removed and hidden lines visible resolution. Typically we like the slider to be around about that sort of position. One of the things that we do see from time to time is that slider gets moved up. Now if I just switch to Windows Explorer here, that particular model that I've got open there is about 91 kilobytes. Okay, you can see that there. If I switch that slider up, and I'm going to move it all the way to the zone just before it gets into the red there, click OK and save, and go back to Windows Explorer. You'll see that it's made a slight increase on there, and this is a fairly simple part, so it's not having much of an impact. So what I'm going to do is I'm going to switch to another configuration. This has got some filleting included in it. I'm actually going to right click on the component here, and I'm going to use the rebuild, save mark, and remove mark and purge data for all configurations to remove the data configuration, and just leave it there for that filleted configuration. And if I save that once again and we have a look at the file size, you'll see that the file size has increased to around about 234 kilobytes. So it's gone up around about 3 times, which is, that's not too bad. Still a small file CAD wise. I've got a third configuration, and I'm just going to switch to that one, which is actually a pattern configuration. And once again I'm just going to purge the data from the other configuration, so we've just got it for that one, to try and minimize the file size increase. And I'm just going to hit save on that, and I'll zoom out so you can see there's actually a pattern of 50 of those bodies there. And if we have a look at the file size now, you'll see it's gone up to about 6 megs. Okay, so having it at the top end of the slider makes a huge difference. If I go back to that slider once more, if I was to drag it up into the red and click OK and do the save operation, which I won't actually do because it takes a little while. Took a screen capture of this yesterday. That's the, you'll see it shortly. It actually blows out to 291 megabytes. Okay. Now if I go back to that and drop the slider back to where we had it before, so roughly about there, and resave and recheck the file size, you'll see that it's dropped down to about 1.7 megabytes. So the difference there is around about 160 times. So if you get into that red zone, you're really starting to look at bumping up that file size significantly. But as a best practice guide, we usually recommend that in large assemblies, you try and keep your slider just to the right of that low, faster region for optimal performance. Alright, so I'm going to switch back to the presentation now. And if we go to the next slide, one other aspect of component impact is with imported bodies. So what I'd be advising here is that we only use clean imported models. Ideally only volume bodies, and so when I say that, I mean that you need to remove extraneous surfacing or curves or point data that can come in with those types of models. What are the best import formats for SolidWorks? Obviously the SolidWorks native file format's the best to get. After that we prefer Parasolid because SolidWorks is built on that kernel. X_T is the file type. That's a text or ASCII based Parasolid. There's also a binary based one, but that doesn't tend to get used that much. After that step, and then ASIS and IGES. IGES is still common, but it's less desirable because its format is quite old. That standard hasn't been updated since about 1996. Scan data can be imported through Scan to 3D. Sometimes people bring in point cloud data and that sort of thing. Ideally, you really want to limit the amount of that data you have in large assemblies, simply because it tends to be a little bit messy to clean up. The other thing about Scan to 3D is that it's 32-bit architecture. It's really only cut out for importing simple bodies, not whole machinery. I have seen people try and do this. It's not really the ideal mode to bring that sort of data in. And if you get people providing files which are really huge scan data files, you probably want to push back a bit and ask for only the data that they really require you to work with. It's about being efficient when working with large assemblies. Alright, I'm just going to quickly switch back to SolidWorks. I just want to go through a couple of things. I'm going to open an imported model. This is actually a step file. I couldn't get it in Parasolid, unfortunately. So I'm just going to go ahead and open that up. And when I'm talking about clean models, it's prompting me to run the import diagnostics on this part. So I'm just going to click yes on that, and it switches to our import diagnostics dialog. And what it's telling me here is that one of the faces is faulty. If I click on that, it will actually highlight in the graphics. You'll see that shortly. And what we need to do is attempt to heal that. So I'm just going to click on the attempt to heal button. SolidWorks goes away and fixes that faulty face. Now that doesn't always work that smoothly, and there are some other things we can do about that. But let me just click OK on that and accept it. So that's imported that body. What we don't want is those faulty faces coming in, because that will cause potential crash issues in large assemblies. The other thing I'd probably mention about this particular model is that if you are importing threads, make sure that you have a simplified configuration where the thread's not present for your large assemblies. The other thing I'll mention here is with imported bodies, sometimes it's necessary to modify geometry. If you miss the import diagnostics on the way in, you can right click on the feature in the Feature Manager design tree and click on Import Diagnostics. It'll take you back into it. This is one to be aware of just because of file size. If I click on that inside face there and click delete that face, that'll remove that face and you can replace that geometry with another surface and trim those boundaries. There is a move face command in SolidWorks if you have your data migration turned on, or you can go to view, insert face, move. It's also there. If you use that move face command to move faces on imported bodies, it will actually increase the file size doubly. And again, if you're doing that, if you're doing large assemblies, it's something to be aware of, because it can impact the processing of that particular component. It's far better to go back into the import diagnostics and actually use that, select the face and choose delete face to remove it. Alright, switching back to the PowerPoint, I've mentioned about the move face there and import diagnostics delete. One other technique we've got with troublesome imports is to save it. If it comes in with faulty faces that can't be fixed, save it out as a parasolid and then re-import that parasolid into SolidWorks. This can also fix other face gap import issues. So it's a good tip to remember if you've got problematic imported files in large assemblies. But the tip here is to make sure that those imported models are clean and don't have errors. Alright, so let's move on to assembly complexity. Assembly complexity is a combination of things, the first of which is the complexity of the components, some of which we've just covered. It can be related to the number of parts, but it's not limited to this alone. The physical size of the assembly, so parts have a size limit of a 1 kilometre cube centred on the origin. Assemblies similarly have a 100 kilometre cube centred on the origin, and if you get close to filling that physical size, then it will impact the performance of the model. The number of mates is definitely a consideration, and we'll talk about that a little bit later in this webinar. Volume geometry, similar to the physical size, basically how much of the limit size is that volume filling in the assembly or the part model. The number of faces, actual faces in the SolidWorks model, is a performance consideration. You can minimize that, I guess, by using better geometry and that sort of thing, or optimizing it. And multi-bodies are also a consideration. 100 parts in an assembly is actually quicker to load than and rebuild than one single part with 100 bodies in it. That might be a little bit surprising, but there you go. Imported components, obviously I've just sort of discussed about that. One other thing to watch out for as well with imported components is their image quality. So similar to our parts, sometimes those imported components that can be downloaded from external websites will have their image quality cranked up to make them look a little bit nicer when they appear on your screen. Assembly features like assembly cuts can also impact performance, especially if there's lots of them, and that's because they're inserted into the Feature Manager design tree after the mates folder. If I just switch back to SolidWorks and let's open up our circular reference example there. If you have a look, I've just got a very simple assembly here with an extruded cut, but it's actually an assembly feature, and it's after the mates folder. And what that means is it will be, or it could potentially be reevaluated after the mates are calculated, and as such re-trigger the mate recalculation. We'll have a look at that in a minute. But I guess what's critical here is just to note that the assembly feature is after the mates folder. Also note that the rebuild icon is stuck in the Feature Manager design tree if issues during the reference update process, so that's why we're going to come back. We're going to have a look at that. Jumping back to the slide again, external references are also an issue. They're probably a good thing to keep an eye on. You need to know where your references are coming from and where they're going to, so that they don't end up in conflict or creating circular references. I guess all of these factors can contribute to performance issues when working with large assemblies. One of the biggest issues though in working with large assemblies is getting them loaded in the first place. So let's have a look at that. So the question here is, what happens when you select an assembly and hit the open button? Well, first of all, it goes to the open assembly, and then it's going to attempt to load all of the reference parts and sub-assemblies. If there's not been any changes since the last save operation, then it will go straight to the graphics creation, and you'll then be done and you can start working with the assembly. If there's been any updates to parts and sub-assemblies and they're listed as out of date, SolidWorks references an internal timestamp in the file to check that. Then it goes through the process of calculating all of the mates and the positions within the assembly. If we have any assembly features like that assembly cut that we just saw, or in context features or component patterns, then it will go through that process of calculating the mates again if they are referenced. Presuming that's successful, then it will go back to the graphics creation, and then it will be done. So just to summarize that a bit in a table, first of all, SolidWorks locates the component files. It seeks out the files required for the assembly. And sometimes with large assemblies, files go missing, those sorts of things, and we need to try and track down where they're coming from. In terms of SolidWorks, if we just have a look at another model here, and we'll just wait for that to load up for the audience. If we're trying to track down those references, if they're not coming through properly, there's a couple of things that we can do to try and track that down. First is to go to the File menu and then go to Find References. And if we click on that, it opens up a new dialog, and it will give us a list of all of the references that are in that assembly. We can choose to copy that list and we can paste that into an Excel spreadsheet so that we can go through and check our list of components. Obviously this is only a small assembly, but the large assembly, it's good to be able to copy that list and put it into an Excel spreadsheet. That way it's not interfering with SolidWorks, and we can sort of navigate that a little bit easier and try and work out why our parts or sub-assemblies are not populating correctly, or indeed just where they're coming from. It's a really good tool for that. If you weren't keen to use that particular method, the other thing that we can do is insert a bill of materials into the assembly. So there's a button on the assembly toolbar or the assembly tab of the command manager. So I'm just going to click on that and insert a bill of materials. It'll ask me to select an annotation view. I'm just going to use the unassigned item ones for this particular example. I can drop that in, and the key here is to just right click on a column and insert a new column, and from the custom properties select the SolidWorks special file special property for folder names, and that will give you the file location for those parts in your assembly. Just going to resize that a little bit so that it's a bit nicer to look at so we can see the part. The other cool thing about doing it that way is that we can click on the row in the bill of materials and see it highlighted in the graphics area, making it a lot easier to identify what components are and where they're located in terms of file management. Alright, so that's just a bit of a tip on managing your files in terms of getting them prepared for loading into large assemblies. If I switch back to the presentation now. So once we've got our files or locations sorted, the next step in the loading process is to load the files into the RAM. I guess the key consideration here is where are your parts located? Are they in fact on a local drive? Are they on a network? Are they on an external drive or a server or PDM, hopefully? And how long is that information taking to get from there onto your desktop? One other consideration is antivirus blocking. Get your IT to check that and whitelist your SolidWorks files if that's the case. All of these things can impact loading large assembly files. The third step in the process is to locate the files respectively in the assembly, and that's the application of the mates. And as I mentioned, step 4, resolve the assembly level features and any in-context references. It's the final step in the assembly resolution. There's an arrow there, and that indicates that if those features are re-referenced, then they need to be re-evaluated. And so it's something to keep in mind, particularly with large assemblies, because that can really blow out the rebuild process times. So in order for us to better manage the loading process of large assemblies, SolidWorks has provided some options on the open dialog to help us out. So let's have a look at those. Basically it revolves around how much information do you need to load. We've got 4 modes. We've got resolved, lightweight, large assembly mode, and large design review. resolved, all the details and references are brought into the model. Lightweight, it does not go through the whole feature manager to resolve each single feature of the parts. Large assembly mode is a collection of system settings that improve the performance of the assemblies. And large design review, it limits the information available for faster loading times. So in a bit more detail, resolved is reasonably self-explanatory. This is where large assembly is going to take the longest to load though. Obviously there are no lightweight components listed there. Everything's pretty much resolved in that type of loading scenario. And that's not the best scenario for large assembly or working with large assemblies. We have lightweight mode. In this particular mode, all parts are loaded without features. Mates are available, and if they're needed, it loads them up automatically when you select the faces that you need. Sideways always recommends to work in the lightweight mode. There are some options under performance, listed under the performance area in system options. We can set it to automatically load components lightweight. Further options there are check out of date lightweight components. There's a drop down for that. If you set it to don't check, I'd suggest that you use that with extreme caution. One of the other options in that drop down is to indicate, and if that does indicate, it'll show a red feather on the feature manager design tree. Normally lightweight is shown with a blue feather when they are up to date. And then the option there, always resolve, out of date components load resolved, even if that automatically load lightweight is set. That way you'll know that those components need to be updated. Okay, large assembly mode. Large assembly mode implies lightweight mode. It sets that automatically when it's dropped in. Under the assemblies in the system options, these are some of the options that you will see relating to large assemblies. And we can set those as we require, so we can set it to do not save auto recover info. We can hide all planes, axes, sketches, curves, annotations. Do not display edges in the shaded mode, and do not rebuild when switching to assembly window. That default can obviously be changed. If you load from the open file, when this threshold is set and a file exceeds that threshold, it will automatically select large assembly mode on the open dialog. You can calculate that even before the file has been opened. And there are some other things that happen when you're in large assembly mode as well. Dynamic highlight is inaccessible, and there's some other things as well. If I switch to the next slide, there's a help link there. If you have a look at the presentation through my indicator a bit later on, you can probably check that out, and it'll tell you exactly what's happening in large assembly mode. I'm probably not going to get time to go through the whole list right at the moment. The other thing I want to mention here is that in 2017 there's been an update, so if I just switch back to that previous slide, you'll see that dialog is for anything pre-2017. On the new 2017 dialog, we've got 4 additional options. So do not preview hidden components, turns off the preview when you select hidden components in the feature manager design tree. Disable verification on rebuild, overrides the verification on rebuild option, which is under the performance page in system options. This is typically used for sheet metal parts, but what this does in this case is it overrides that. that particular option is very CPU intensive, and by checking that option, it removes some extra checks that it does, and will speed up your performance in large assemblies. Optimize image quality. It downgrades the image quality in the assembly to speed up some performance, but it doesn't actually affect the underlying parts, and I'll talk about that a little bit later. Suspend automatic rebuild. That does exactly what it describes, and we'll talk about that in rebuilding in the mates section. Right, moving on. Large design review. This is a fairly significant mode when working with large assemblies, because it doesn't give you an access to a lot. It does give you an active feature manager. It allows you to selectively open lightweight from a right mouse button click. It does allow you to measure and section. You can show and hide components. You can take snapshots, make walkthroughs, but it's really only a graphic view. And again, I've put a link in there to the help location where you can check out exactly what this does and doesn't do. And I guess in summary, when do we use these particular modes? Resolved when full data is required and not available from lightweight mode, so if you need to access properties. Lightweight is always recommended anytime, anywhere for large assemblies, and if you're working in large assembly mode, then as I mentioned before, it's in lightweight anyway, so large assembly mode is really where you need to be at. And large design review is really for viewing, doing fly-through, or working on sub-assemblies. During the loading process, one of the most critical steps is step 3, to locate the files and the application of the mates. So if we start talking about mates now, the loading and solving of mates. So during loading, mates are all solved together, flexible and resolved as part of a matrix. If you have a look at the mates folder in a SolidWorks assembly, it's just one big folder. Now you can put subfolders in there, but they're all effectively one big matrix of numbers. If you add a single mate, it increases that matrix element size exponentially. So if we're talking about a minimum mate count of 300 mates per assembly, that's 90,000 elements in the matrix. If we bump that up to 301 mates, it goes up to 90,601 elements. So every time you add a mate, you're significantly increasing the size of that matrix, and consequently bumping up the time that it takes to process all of those matrix elements. Some of the activities that trigger solving all of the mates, and you might find this list quite surprising. Every time you rebuild the assembly, you're going to solve all of the mates. Every time you force regen, Control Q, you're going to solve all of the mates. If you insert a new component, you'll be solving all of the mates. If you move a component in the assembly, you'll be solving all of the mates. And finally, if you add a new mate, and that includes locking the rotation, you'll be solving all of the mates in that matrix. And for that very reason, I always recommend that you try and minimize the amount of mates in an assembly, and that usually means building more sub-assemblies. Mate processing. So we've looked at how when the mates are processed. This is more of a how the mates are processed. And there is a knowledge base article that you should be able to access that describes this process. It's pretty much what I've got written here, but there is some additional information. First of all, it passes the mate group and identifies the order the mates need to be processed and checks the interdependencies between the components and sub-assemblies. It processes the mate group in that order derived by that pass process, It verifies the validity of the process mates. If there are any errors are found, processes the mates again in the order derived from the pass operation. If the situation there is no valid solution to the mate passing process as such, the program will select the least bad solution, and in order to derive this least bad solution, all possible mating schemes will be considered. So in large mating schemes, with large assemblies, if there are any errors, the passing process is going to take a considerable amount of time. And that's why we always suggest not to leave mate errors in SolidWorks. And this also applies to parts. So when I talk about clean imported geometry and tidying up sketches that have got those little overhanging errors and things in there, make sure everything's clean in your large assembly. Don't leave errors in them. In terms of mating performance, the number of mates, I've already mentioned that 300 was around about the suggested. It's not necessarily a hard and fast limit. That information comes from a document that was published back in around about 2009 and reviewed in 2010. The previous knowledge base article, 06266, which I mentioned about how mates are processed, refers to this, or is referred to by S-043917, and in that it also says that the total number of features in the assembly is actually more important. So if you've got more than 3,000 total features in any assembly, then that's probably going to affect it more than the number of mates. But as I've already mentioned, you'd probably want to try and keep your mates in any assembly minimized and build more sub-assemblies. The mate types also have an impact on performance. Standard mates usually take around about 1/10 of the time of an advanced mate to process. Mechanical mates, you can pretty well assume that they'll take as long as an advanced mate, but probably longer, depending on complexity. And one other consideration is the depth of the mate chain. You might be a little bit cluey or questioning what is exactly a mate chain. Well, really it's just how many mates do you have to get back to the ground mate or the primary mate in the system. You probably want to try and minimize that depth so that you haven't got mates upon mates upon mates, because they do solve in a specific order, and if there's a long length of them, then it's going to take longer to process. And one other key thing to remember here is to always mate fasteners to parts, not the parts to fasteners, simply because of that depth of the mate chain issue. Fasteners should be things that can be removed without impacting the assembly. They shouldn't be actually holding it together. So best practices, just to summarise for mate performance, is to use standard mates where possible. If you get over-defining mates, make sure you correct those as soon as they appear. Use rigid sub-assemblies. Sub-assembly mates are not solved when the main is rebuilt. You can test that just by dropping your top level large assembly into a dummy assembly. You shouldn't need any mates to hold that in position. It should, if you use a fixed mate, it should just fix itself there, and you shouldn't need anything to define those positions further. You use more sub-assemblies. I think I've probably mentioned that enough times. Use fixed conditions. You can get the correct position without using any mates. So normally when you drop your first component or sub-assembly into an assembly, you should be able to position that using a fixed mate at the origin, rather than trying to mate it. And if you set that up beforehand, then you should be able to just drop it in using a fixed condition. Do not mate to temporary axes. There's a long list of issues with doing this, so make sure you're not using that in large assemblies. it's going to cause you a bit of grief. Reduce the mate chain depth to a minimum. Just to round out, one last tip for mate performance. There is an option when you put an assembly or a part into an assembly where you can mate the origin with the align axes option. Using origins to mate does not reduce the complexity of the mate matrix. It will only reduce the number of mates in the feature tree, so you only get 1 instead of 3. SolidWorks still creates the 3 coincident mates internally to the hidden planes, so there's no difference in rebuild times for applying the 3 coincident mates to the major planes or mating the origin with the align axes options if you're doing things that way. Alright, file versions. Got a little bit of time to quickly talk about this. Convert all files to the latest version. In SolidWorks 2016 they introduced a tool as part of Task Scheduler called the Upgrade Assistant. You can use this to verify that your files will upgrade to 2016 for 2016, or if you're in 2017 you can use it to check whether they'll come into 2017 nicely. That's a good way to convert all your files. Or you can use our Sharp Task tool. If you want to know more about that, happy to help you with that if you just want to drop me an email after the webinar. But that is a automation tool that we can use to do many things, but one of those is to convert files to the latest version. Files from other releases converted in the background on load. So when you're bringing in files that haven't been converted to the latest version, SolidWorks does convert those when you open them up in the assembly, and it will do that every time you open them. So that could cause significant performance hits every time you're opening that large assembly if they're not converted to the current version. Also, you probably want to check the versions on imported third-party files from vendors, because typically they tend to be older versions created from macros, so something to keep an eye on there as well. Common issues, so really just summarising what we've had a look at. Make sure your image quality is not too high, and particularly check this in your templates as well. That's often a good place to set that, so that when you're creating new parts and sub-assemblies, that image quality is reduced. And for parallel tessellation, there is an option which I talked about, and let me just switch quickly to SolidWorks to look at this. If we go into an assembly file and look at the document properties and go to the image quality, you'll see that there's an option there, apply to all reference document parts in SolidWorks. As far as I know, currently in 2017 this option is not working as it should. To work around that, again, you can use our Sharp Task tool to update those files' image quality, and that is the current workaround for that issue. Main assembly only contains folders. Quite often people will use folders instead of building sub-assemblies. That is a big no-no in large assemblies. Please build more sub-assemblies. Assemblies that have more than 300 mates on the highest level, again I said that, I've checked that with SolidWorks. They suggest that there's probably no hard and fast limit now that we're in 64-bit operating systems, etc. If you're operating on SolidWorks 2010 or earlier, then maybe keep that in mind, but now it's probably not so much an issue, it's more of a guideline. And again, I would say that if you're getting over 300 mates, then it might be time to look at some more sub-assemblies. Assemblies with general model errors may errors in context reference issues. Make sure you're checking those things out. I'm going to talk about some tools that look into that in the 4th webinar. Too many details, components which have thousands of faces. Usually this is import geometry, but again, as I mentioned with threads, make sure you have a simplified configuration that removes any unnecessary faces for your large assembly configurations. Files are not converted to the latest version, just talked about that. And imported components have faces with errors. That's what we started off with. SolidWorks has the best performance when working with volume bodies only. And that kind of wraps up the presentation for today. I'm right on 58 minutes. Probably have some. Alright, looks like that's just about it for now. Once again, thank you to everyone for attending. If there are further questions, please drop me an email and I'll be more than happy to try and help you out with any large assembly issues that you might be having. And if you can't get hold of me because I'm in training or something, then yeah, email the team as well. Alright, thanks once again, and have a good afternoon.